is going to be the next video in the structure of atom. So we are almost coming towards the end of the chapter. We have discussed in the last video about de Broglie's wavelength and Heisenberg's uncertainty principle, following which we understood there is Schrodinger's wave equation. And if you solve that wave equation, which is beyond the scope, but imagine you solve that, you are going to get a set of four numbers which are called as quantum numbers. Okay, what are these quantum numbers? These are numbers which are used to give exact, I cannot get exact, or let me say to give complete info, to give complete info about the address of an electron. Alright, in an atom. So you know what is the structure that we currently understand? There is nucleus, which we know it is at the center. And surrounding the nucleus in definite orbits, you have electrons. And we also studied in Niels Bohr's theory that the electron in the orbits, if they absorb energy, they will get excited, they'll go to an excited level, and then they fall back to the lower energy level. Also, we have understood that it is not possible at a time to predict its position as well as momentum, and that leads to an error if we try to do so. So we only talk about probability of finding an electron. What is the chance of finding an electron here? What is it here? What is it here? That's what we talk about. And in order to make things easier for us, we try to map the location, or even if you talk about probability, we try to get into that probability aspect using four quantum numbers. It is just like if I have to tell you your address, you have to give details like which state do I live, which district, which area, which road, which apartment, and things like that. Correct? So we are trying to locate the address of an electron inside an atom using the set of quantum number. And how did we get these quantum numbers? When you solve that Schrodinger's wave equation, h cap psi is equal to E of psi. When you solve that, that psi variable is going to give you all the four quantum numbers. And we don't have to get into the details how to solve, but we only have to know what are the four quantum numbers. Let me write the set of quantum numbers. Alright, the first one is called as the principal quantum numbers, which I had already mentioned in the previous videos. This is the principal quantum number denoted by L, and the second one is what we have as the azimuthal quantum number, which is denoted by lowercase m. And the third one is the magnetic quantum number, which is denoted by m. And the last one is spin quantum number, which is denoted by S or ms. Now the three set you get it from the Schrodinger's wave equation. Okay, now this you will not get because this has got a fixed value. I'll come to that. Now these are like numbers. Like now how do you relate it? If you consider atom to be an apartment, principal quantum number is like the floor, each floor, first floor, second floor, third floor. Azimuthal quantum number are like flats. In each floor there are different flats. You keep this view in mind, it becomes easier for you. Magnetic quantum number is like basically the rooms. Now see, when we tell our address, we only stop at the flat level, right? But here we are trying to find the exact location where the person is currently. So even if you give just the flat, that person might be anywhere in any room. We want to know the exact location. That's the reason we get inside the flat, and this number tells you about the room, and this is basically it is talking you about the spin. Basically I talk about it. Okay, so have this view in mind, it becomes easier for you to understand. First, let's get started with the principal quantum number, which we already know. Principal quantum number denoted by n is your orbit or the shell or the energy levels. Whatever we have studied that electrons are in definite orbits in surrounding the nucleus, that itself is your principal quantum number. Correct? So what it represents, size and energy of a shell. Correct? It represents size. So based on that, you know at what distance you are from the nucleus, and each orbit has a definite energy. I told you that whichever is closer has least energy, and as you go away, the infinite shell has the maximum energy, and that maximum energy is 0. So if the principal quantum number increases, the size also increases, the energy also increases. I just mentioned this. And what is the maximum electrons? This is something you already studied. Maximum electrons in a shell is going to be 2n square. Let us also understand how did we get this. Only after we understand these three numbers, you will be able to understand why is it 2n square. Alright, so now if I give values to it, if I say n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. So now, don't just limit yourself to 4. This is what we are studying. There are infinite shells like I mentioned. This is what we call as K shell. This is something which is closer to the nucleus. L shell, M shell and N shell. These are the names. So what will be the number of electrons? If I put n is equal to 1 here, it will be 2. 2 into 2 square will be 8. 2 into 3 square will be 18. 2 into 4 square will be 32. These are the maximum number of electrons in each shell. So you can write this to be the nucleus. I mean, I'm just drawing this way. Okay, it's the complete circle, but I'm just writing this part because it's easier for you to understand. So this is your n is equal to 1, this is 2, this is 3 and this is 4. That means this is K shell, L shell, M shell, N shell. Okay. So this is what the closer it is. As the number increases, the size is also becoming more, the radii, and the energy is also becoming more. And we have already studied how do you get the radius of the nth shell. Like n is equal to 3. How do I get that? It is R naught n square by c. Okay, n square by c, angstrom. Alright, and we know this. I have told you what is the formula for R naught also. What is the value of R naught? And what is energy of an nth shell? In terms of EV, if I have to write, minus 13.6 z square by n square. Alright, so this is the energy. This is about principal quantum number. Nothing much for me to explain because this is something that we already know. Let's now talk about the second quantum number, that is azimuthal quantum number. I will retain this figure, alright, and then we will complete this figure, and I want you to embed this figure in your mind. If you embed this figure into your mind, this entire chapter is becoming very, very smooth for you, because this part will definitely have one question in the final exam. I can guarantee on that. So there will be one question from the previous part, all the while whatever we have studied till now, and there will be one or two questions from this section. Okay, now having understood principal quantum number, let us talk about the next quantum number which is derived from the Schrodinger wave equation, and that is azimuthal quantum number denoted by L. And I told you just visualize them as flaps in each floor. Okay, now what are they called? This is for your analogy, they are called as subshells. Okay, azimuthal quantum number, like each shell is divided into subshells, and azimuthal quantum number is the one which tells me about the subshells, which is the further division of shells. Now please understand, all this are something which are imaginary, alright, we visualize them to be like that. Alright, so let's go further. Now the value of L depends on n. So the value of L is 0 to n minus 1. Okay, every value of L will represent a particular subshell. Every value will represent a particular subshell. What is the meaning of this? I tell you. Now if you are talking about n is equal to 1, that is K shell, what will be the value of L? Write it, 0 to, n is 1 here, 1 minus 1 is 0, that means L is 0. And if L is 0, this has a particular thing. Whenever you say L is 0, it means it is the S subshell, lowercase s. Okay, so L is equal to 0 has a fixed value. Just like if I say, pi has a fixed value, 22/7 or 3.14, whatever, it's an irrational number. L is equal to 0 means it's an S subshell. That means in the first shell, there is only one subshell. Okay, so this is my S subshell. So imagine it to be like S flat. Okay, so there are different kinds of flat. One kind of flat is S flat. And S subshell has a shape also. This S subshell is spherical in shape. Okay, so S flat is spherical in shape. Alright, I'm just writing it here this way, but otherwise this is this. Now, if you say n is equal to 2, what will be the value of L? 0 to n minus 1. So 0 to 2 minus 1, that means 0 to 1. 0 to 1, so that means it has got two possible values. And I told you L is equal to 0 is always a S subshell, and L is equal to 1 means it's a P type of subshell. So this has got two subshells. Okay, so this has got two subshells, S subshell and a P subshell. It is like, generally in an apartment, all the floors will have the same number of flats. But this is a special kind of apartment wherein the first floor has got one flat, the second floor has got two flats. Alright, and what is the shape of this P kind of flat? It will have a dumbbell shape like this. Okay, so remember that. And we will draw the shapes and all after we understand all of this. N is equal to 3 is M shell. So it will be 0 to 3 minus 1. That means 0, 1 and 2. 0 is S, 1 is P and 2 means D. So 2 is D. So it has got three subshells, S flat, P subshell and D subshell. And what is the shape of this D flat? It's a double dumbbell like this. So you can imagine two dumbbells which are placed like this. Or you can imagine four balloons which are, having somewhat this kind of shape. Alright, so yes. Now let us talk about n is equal to 4, which is your n shell. It will be 0 to 4 minus 1. So L will be 0, 1, 2, 3. That means this will have S, P, D flat and another kind of flat which is F flat. Now F flat shape, let us not bother, it's slightly complex. S, P, D and F. And if you're talking about fifth shell onwards, you will only be dealing with these flats for now. Okay, so this is the picture I want you to imagine. If this picture is there in your mind, that it is S, SP, SPD and SPDF. And of course, we will talk about orbital also, but that's next level. At this stage, this is what you need to remember. Okay, so what are these SPDF standing for? Let me write that also. S stands for sharp. P stands for principal subshell. But we do not have, you just have to know this. Nobody remembers this. This is diffuse subshell and F is fundamental subshell. These are the expansions of these SPDF. What will be the total number of subshells? Total number of subshells in a shell is equal to the shell number. Very important. It can be asked for 1 mark. What is the meaning of that? Total, how many subshells are there in each shell? First shell has got one subshell, second shell has got two subshells, third has got three. So that is what I mean. Alright, so number of subshells in a shell is equal to shell number. These are the shell numbers. So first shell has got one subshell, fourth shell has got four subshell and so on. Okay, so shapes I have already told you. This is spherical, this is dumbbell and this is double dumbbell. Okay, now there is something called as orbital angular momentum. So because it is going around the nucleus in a definite orbit, it's just like a circular motion. In physics, we have studied about angular displacement, angular velocity, angular acceleration. What is this angular momentum? Angular momentum in orbital is nothing but mvr, and that is given as L into L plus 1 under root h by 2 pi. What is the meaning of this? This is something that we have done in Niels Bohr theory. Angular momentum is mv into r. mv is the linear momentum, you multiply by r, this is angular momentum. Is an integral multiple of h pi 2 pi. That integral multiple, now we are understanding what is the value. It is L into L plus 1 under root. That means if you are talking about a P sub shell, now P sub shell can be here, here or here, anywhere. P is flat, which is there in all the floors except for the first floor. What will be its orbital momentum? Orbital angular momentum of a P sub shell is PL is equal to 1. 1 into 1 plus 1 into h by 2 pi. So this is root 2 h by 2 pi. Alright, so this is what you get. For a P sub shell, it's going to be this. Alright, so this is about your azimuthal quantum number. That's the second type. It talks about the flat. This is the analogy I've given you. And remember, the number of flats in each floor is equal to the floor number. Okay, so yes. Now let's go to the third kind of number. That's going to be your magnetic quantum number. I will retain this figure again because I'll be updating this figure itself. So let's talk about the third quant, which is called as the magnetic quantum number, represented by lowercase m, and that is like your room, okay, and technically it is called as orbital. So each shell or an orbit is divided into subshells. Subshell is divided into, so shell is divided into subshell and subshell is divided into orbital. Okay, so this is like your flat, this is like the floor, and this is like your flat, and these are the rooms in a flat. Alright, so what it tells you, what is this orbital? It is the closest region where you can find the nucleus. So it basically represents, what is an orbital? It represents the orientation of electrons. Okay, orientation of electrons in a 3D space. So it's like, if I say I am in this flat, it is fine. But if I specifically say I am right now sitting in this room, the chances of you finding me are more. Because if I say just a flat, I can be in the kitchen, I can be in the living room, I can be in the washroom, correct? But if I say that I'm in this room, you are coming closer and closer towards me. I mean, you are finding me, the chances of you finding me are greater here. Alright, so it is a 3D region around the space where, and what is an orbital? It represents the orientation, which means it is the 3D region where the probability of finding electrons is the maximum. Okay, so I can say I live in Bangalore, I can say I live in this area, I can say I live in this apartment, but what is the closest? Where are the chances of you finding me the maximum? If I tell you that I am in this particular room, that's the closest, right? So this is exactly what is happening in the case of electrons as well, correct? And now let us talk about the different set of values for. Now before we talk about that, I told you what is a node. Node is a region where there is no chance of finding electron, or chance of finding electron is 0. There is also something called as the nodal plane. And what is this nodal plane? It is the imaginary plane. Everything is imaginary plane which cuts the orbital which does not have any electron, in simple words. Okay, so if you are talking about a region, it's a node. If you are talking about a plane and you're sure that that plane what I have chosen, I can vouch for it that there are no electrons there, I can never find electrons in this region, then we call it as a nodal plane. I will explain you after we are done with this part. That time it will be easier for you. Alright, now what will be the value of m? M is dependent on L and it ranges from minus L to plus L. Alright, N is there, L depends on N, correct? So it is 0 to N minus 1. And this depends on L, that is minus L to plus L. Let us now write it for everything. For K shell, N is 1, correct?
So what will be L value? L value will be 0 because it is 0 to 1. And L is equal to 0 is S subshell. Let us write the value of M. M will be minus 0 to 0, which is 0. That means L is also 0, M is also 0. What is this? This only tells you that it is S orbital. Alright. So it's like, imagine there is an S-shaped flat, and inside the S-shaped flat, S-named flat, I'm having a S orbital, S room. Alright. So it has only got one S orbital. Okay. Now if you're talking about L shell, that is n is equal to 2, L is equal to 0 and 1. For each thing you will have to write M. So M will be 0 here and M will be minus 1 to 1, which is minus 1, 0 and 1. Are you getting it? Because it's minus L to plus L, minus 1 to plus 1. What is the meaning of this? See, what is this? L shell has got two subshells, S and P, correct? As mentioned by the azimuthal number. For each subshell, you have to talk about flats. So this has got only one S flat, and this has got how many? 1, 2, 3. Correct? This is what we call as 3P rooms. Okay, so the P flat has got 3 rooms. And how do we write those 3 rooms? We write it as Px, Py and Pc. Okay, so this is how you write. So each P orbital, each P subshell has 3 P orbitals. Remember that. Okay, so this is your Px, Py and Pc. It can be in any order, doesn't matter. Alright, so now let us go further and talk about M. For M, what will be L? 0, 1 and 2. This I already know. M is 0. If it is 1, it is minus 1, 0 and 1. If it is 2, minus 2, minus 1, 0, 1 and 2. Now look at that. This is your S orbital. This will be your 3 orbitals, 3p orbitals, and these are your 5d orbitals. So if I have to just tweak this diagram, this is how I'll be doing it. So S has only one S. P will always have 3 rooms, right? So this is again Px, Py and Pc, and D has got 5 rooms. Okay, so now what will be the names of that rooms? I will tell you. For D, dxy, dyz, dzx, dx square y square and dz square. These are the 5 rooms. Okay, we will talk about this in detail. For now, let's talk only remember these names. So this is dxy, yz, zx, x square minus y square and z square. It can be anything. You can call this also as dyz, but I'm just naming it this way. Alright, so yes. Now let us talk about the last k, n is equal to 4, that is n shell. So what will be your L value? 0, 1, 2, 3. 0 means it is S orbital. Okay, this means it is 3p orbitals. Correct? And what are those? Px, Py and Pz. 2 is like minus 2 to plus 2. That means there are 5d orbitals. So it will be dxy, dyz, dzx, dx square y square and dz square. And if it is 3, suppose, that means what is the F kind of flat, how many rooms it has, how many orbitals? It will be minus 3 to plus 3. That means it will be minus 3, minus 2, minus 1, 0, 1, 2 and 3. That means there are 7 F orbitals. So let us change it here as well. So all the P flats will have always 3 orbitals. The D will have 5 orbitals and the F will have 7. Alright, so this is how it is. So this is P, this is D and this is F. I want you to get this picture in mind. Alright, so this is about orbitals. So what did we learn? For every shell, it is divided into subshells. And the number of, how do we get that subshell in each cell? It is dependent on the shell, that is from 0 to L minus 1. Okay, L is equal to 0 to N minus 1. And the number of subshells in each shell is going to be different. It is not the same. Point number 1. Then We also understood how to get these subshells. We have already studied this. L is equal to 0 is always going to be a S subshell. 1 will be a P subshell, 2 is going to be a D, and 3 is going to be a F. Now for every subshell, we have something called as orbital, which is the 3D region where the chances of finding electron is maximum. And this is how we write it. Now let us talk about little more before we get into spin quantum number. I will complete spin quantum number, and we can continue with the next topic about how do you write the configuration, what are the different rules and everything in the next video. Alright, so now in a subshell, how many number of orbitals? Look at that. In a subshell, how many orbitals? If I say P3 and all that. So in general, I can say it is 2 into L plus 1 orbitals. So if I say it is 3, I know there are how many? 5 plus 3 plus 1, which is 9. Let us put 3, I will get it, correct? So it is 2 into L plus 1. Okay, so L it is. L is what? L is here in a subshell they are talking about, right? How many orbitals are there? So L here will be, in the third shell, L will be equal to 3. So that's how you get it, right? So yes. And also, in a subshell, how many orbitals? These are the orbital. How many orbitals will be there? Again, there will be n square orbitals, right? So this is having, no, this is this side only. Okay, so if you're talking about subshells, you will be having n square orbitals. Correct? So this is what it is. Okay. So first has got 1, second has got 4 because it's 2 square, third has got 9 because it's 3 square, and fourth one has got 16 because it's 4 square. Alright. Yes. Now also understand that in each orbital, okay, in one orbital, it is like a 2B. I told you orbital is like a room, so you can remember it to be like a 2-bedroom because one orbital can hold only 2 electrons. So feel this is the nucleus. This is one orbital. Here I can accommodate maximum 2. After that it will come, and that is how it fills. We will understand all of that. Alright, so one orbital will hold 2 electrons. Remember that. Okay. Now let us draw the shapes so that you are familiar. So S orbital, how does it look like? S subshell is spherical, S orbital is also spherical, and it just looks like this. This is one end, this is the second one, and so on. Let's now talk about the P orbital. P, there are 3 P orbitals, right? I have told you how it is, and the values can be 0 and this. It can be anything, it's not like Px is minus 1. Alright, and there are 3 p orbitals. What is this px? If this is your x-axis and this is your y-axis, px is a dumbbell along x-axis, and py, if I say x and y, this is a dumbbell around y-axis, and if I say pz, this is x, y and z, it will be somewhere here. Now it's not like it's in the air, it's just in 3D. It is actually coming on this. Correct? So this is how it is. These are your P, X, Y, X, Z and P, X, P, Y and P, Z. Alright, so this is how it is. Now what will be the modal plane here? The modal plane will be your YZ plane. What is the meaning of this? Please feel this. Okay, now this is my x-axis and this is my y-axis. The orbital is here. One part is here and one part is here. Any plane like this, YZ plane is this. This will be a nodal plane, right? Because the electrons, see, the electrons are now here. So if I have a plane which is cutting like this, exactly like my hand, electrons are always in these regions. So my hand will never have electrons. That's why it is the nodal plane, YZ plane. If it is along y-axis, what is the nodal plane? XZ plane. And if it's along the z-axis, XY is the nodal plane. Alright, so this is about the shape of p orbitals. Now let us talk about the shape of d orbitals. You have 5 d orbitals because d subshell is for L is equal to 2, and you can write from -2 to +2. Okay, now you can divide it into two categories. The dx, dxy, dyz and dzx, they are called as lobes, they are called as non-axial. Non-axial orbitals, which means that the lobes are not along the axis, the lobes are between axis or along the coordinate. Okay, between the coordinate axis. Yeah, the lobes are between the axis. That's fine. Yes, and that's why they are called as non-axial. Lobes are between. They are not on the axis. Whereas if you talk about dx square y square and dz square, they are called as axial because the lobes are on the axis. I will talk about it. What is this dz? Look at that. This we are trying to write a dxy now. Okay, so this is your x, y and z axis. X, y means it is between x and y like this. You have to feel it in 3D. So imagine this is x, y and z. When I say dxy, one is here, one is here, one is here and one is here. Okay, so this is how, what is your dxy. What will be the nodal plane in that case? X and y axis. Think about it. X axis and y axis will be the nodal plane. I'll explain what is this. Nodal plane is that plane which does not contain electron. If you are saying it is like this, obviously along the x-axis you cannot find electron, right? Because electrons are only found in the orbital. That's why x and y-axis will be the nodal plane. Okay, so let's draw it for x, y, z. So I will just write this as x and z here because otherwise it is difficult to draw into. Okay, so I'm always going to draw the same shape, but remember it is x, z now. And what will be the nodal plane? Nodal plane here will be y and z axis now. Okay, so what is it? X, z is like, horizontal. It is sleeping like this. The lobes are like this. Okay, so obviously your y-axis and the z-axis will be a nodal plane. And look at that, they are all between the lobes. Do you see that? It is not along the axis. It's between the lobes. That's why they are called as non-axial. And at last, z and x and z. Okay, so the lobes are like this. Correct? So, which will be the nodal plane? X and z axis. That is about the non-axial. Let's talk about axial. What will be the shape of this? This is x and this is y. This is how the shape is. X square, y square. And it is between the lobes. Right? So, lobes are on the axis. And at last, it will be your, this has got two nodal planes. You can cut one here and one here. Okay, and the last is dz square. And dz square looks like this. So there is a ring at the center. On that top of ring you have your lobe. So this is dz square. And this is the z axis in that case. Okay, and it doesn't have a normal node. Okay, so that is about the orbital. Okay, so you had orbits which are divided into subshells. The number of subshells will be equal to the shell number. Each subshell is divided into orbital, which is the closest area where you can find the electron, probability of an electron. Correct? So the value of the orbital depends on the value of the subshell. If you're talking about s, it will have one s orbital. If you're talking about p subshell, it will have 3 p orbitals because the orbital number ranges from -l to +l. Okay, so similarly there are 4 and there are 3 here and there are 5, 3, 5 and 7. Okay, so that's about orbitals. The last part here will be about the spin quantum number. Spin quantum number is the only one you are not getting from the Schrodinger wave equation because they have a fixed value. Alright, so this is about the spin quantum number. It represents the spin. Electrons, when they are just like your Earth planet. The planet is going around the sun and it is also spinning and going. So it is like this. It is moving and it is spinning. It's moving, it's spinning. The number which tells you the spin is what we call as the spin quantum number. So I told you Let us say there is an electron here. An orbital can hold 2 electrons. I told you that it's like a 2 bed, okay, double bed. So 2 electrons it can hold. Now what distinguishes them both? Because ultimately we are trying that each electron has got a unique address. So both the electrons in this part will have the same shell, same subshell and same orbital. So in order to distinguish between themselves, the concept of spin was introduced, and it has only got two values, plus half and minus half. Plus half is when it is clockwise, minus is when it is anti-clockwise. And just like you had orbital momentum, you have spin angular momentum because of the spin, and that is s into s plus 1 under root into h by 2 pi. Okay, so let's summarize this. Total number of subshells, if you're talking about a shell, see, it is just that, the electrons will keep spinning, right? If you're saying there are two electrons in one room, that is your S room has got two electrons now. One of them will be spinning clockwise, one of them will be spinning anti-clockwise, and we give the values accordingly. Alright, let's summarize. So you have a shell, the number of subshells is equal to the shell number, that is n. Okay, the number of in the shell also, if you are talking number of orbitals, that will be equal to n square, and the max number of electrons will be equal to 2n square. Now let us understand why. Look at that. This part I think it's fine. Number of orbitals is n square. That also I told you, right? 2 is 4 here. 3 square is 9. Here you are having 2n square. 4, 16 into 2, 32. Yes. Now, maximum electrons, why it is 2n square? Because each orbital can hold 2 electrons. One will hold 2 electrons, n square will hold 2n square electron. That's the reason you have 2n square. Or in other words, you can take any random one, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 orbitals, 9 into 2 will be 18. There are 4 orbitals, 4 into 2 will be 8. That's why it can hold 8 electrons. It's like a double room. The orbitals are like rooms, and the capacity of a room is 2 electrons maximum. Okay, so I hope this hierarchy is fine to you. So we have different shells. Each shell is divided into subshells. The number of subshells is equal to the principal quantum number, and for each value you have a definite kind of subshell. So the first shell has got only one S subshell. The second shell will have two subshells, S and P. The third will have three S, P and D, and the fourth will have S, P, D, F. And each subshell is further divided into orbitals. Like flats are divided into rooms, it's divided into orbitals. And the number of orbitals for a given shell number will be n square. Alright, so that's about the number of orbitals. And the max number of electrons in each will be 2n square, because I have n square orbitals. One orbital can hold 2 electrons, and hence it is 2n square. Alright, so before we proceed to the next topic, I will end this for today. We will do a couple of questions here and then proceed to the principle, some of the major principles and rules we need to understand before we talk about the structure. Exactly understand the flow of electrons in all these different structures, that is subshells, shells and orbitals. We will talk about it till the orbital level. Now everything is going to be till the orbital level, because now we are coming closer and closer towards finding where can electron could be in an atom. Yes.